Welcome to the DX Today podcast, your daily deep dive into the AI ecosystem. I'm Chris, and joining me as always is Laura.
Hey, Chris. Really excited about today's topic because it touches on something that affects literally every company running AI models right now, which is the insane cost of memory.
Yeah, so today we're talking about Google's TurboQuant, which is this new compression algorithm that came out of Google research, and it is genuinely shaking up the entire AI infrastructure landscape in a big way.
Shaking up is almost an understatement here, because what TurboQuant does is shrink the memory footprint of large language models by at least 6 times, and here's the kicker. It does this with zero accuracy loss and no retraining required.
Okay, so let's just make sure everyone understands why that's such a massive deal. Because when we talk about running these large language models, memory is one of the biggest bottlenecks and cost drivers in the entire pipeline.
Exactly right, so think about it this way. When a model like GPT-5 or Claude is processing your request, it needs to store what's called a key value cache, which is essentially the model's working memory of the conversation so far.
And that working memory gets enormous really fast, especially as the context windows keep getting longer and companies are pushing into million token territory and beyond, which means you need more and more expensive GPU memory.
Right, and we're talking about high-bandwidth memory chips, HBM chips, which are manufactured by companies like Micron, Samsung, and SK Hynix, and those chips are incredibly expensive and in extremely high demand right now.
So along comes Google Research with TurboQuant, and they basically say we can compress all of that working memory down to 3 bits per value without losing any measurable accuracy. So walk us through how that actually works technically.
Sure, so the core innovation is something they call PolarQuant. And what it does is take the data vectors in the key value cache and randomly rotate them in high-dimensional space before quantizing them down to very few bits.
Now, I want to make sure I'm following this correctly, because random rotation sounds like it would introduce noise or errors, but you're saying the math actually works out so that the rotation preserves the important information in the data.
That's exactly right. And the mathematical elegance here is beautiful, because the random rotation distributes the information more evenly across dimensions, which means when you quantize down to fewer bits, you lose less critical signal than you would with naive compression.
And then there's this second piece to the puzzle that they call QJL, the quantized Johnson-Lindenstrauss algorithm, which handles something about eliminating hidden errors in the compressed representation, right?
Yes, so QJL uses just one additional bit per value as a residual correction. And what that does is eliminate the systematic bias that quantization normally introduces. So your attention scores stay accurate even at extreme compression ratios.
So when you put PolarQuant and QJL together, you get this system that can compress the key value cache down to 3 or 4 bits per value from the original 32 bits. And the model still performs just as well across all the benchmarks.
And not just one type of benchmark either. They tested this across question answering, code generation, and summarization tasks. And there was no measurable accuracy degradation, which is honestly remarkable for that level of compression.
Now let's talk about the raw performance numbers, because those were really eye-catching to me, especially the speed-up figures they reported on NVIDIA's high-end hardware, the H100 GPUs that everyone is fighting over.
Oh, the numbers are wild. So on NVIDIA H100 GPUs using 4-bit TurboQuant, they measured up to an 8-time speedup in computing attention logits compared to the standard 32-bit unquantized approach, which is a staggering improvement.
An 8-time speedup is the kind of number that makes CTOs sit up in their chairs, because that directly translates to either serving 8 times more users with the same hardware or cutting your GPU fleet by a massive amount.
And VentureBeat reported that the cost reduction could be 50% or more, which when you're talking about companies spending tens of millions or hundreds of millions of dollars a year on GPU infrastructure, that's a transformative amount of savings.
I love how TechCrunch called it the Pied Piper of AI, which is a reference to the Silicon Valley TV show where the fictional startup invents a revolutionary compression algorithm. And now life is literally imitating art in the most Google way possible.
That reference is so perfect because in the show, the compression algorithm disrupts entire industries, and that's exactly what we're seeing play out in real time with TurboQuant's impact on the memory chip market and the broader AI hardware ecosystem.
All right, so let's get into that financial impact, because this is where the story gets really dramatic and honestly a little scary for certain companies that have been riding the AI hardware boom for the past few years.
So here's what happened. When the financial markets fully digested the implications of TurboQuant, memory chip stocks got absolutely hammered, and we saw billions of dollars wiped off the market capitalizations of major players like Micron Technology.
And the logic is pretty straightforward, right? Because If you can run the same AI workloads with 6 times less memory, then the demand for these incredibly expensive high-bandwidth memory chips should theoretically drop significantly over time.
Exactly. And it's not just Micron, Samsung, and SK Hynix also felt the pain because these three companies essentially control the global supply of HBM chips. And the entire bull thesis on their stocks was built around insatiable AI memory demand.
Now, I want to play devil's advocate here for a second, because we've seen compression breakthroughs before, and the demand for compute and memory has always found a way to grow. So is this time really different, or will Jevons paradox save the chip makers?
That's a great question, and I think the honest answer is probably a bit of both. Because, yes, Jevons paradox suggests that efficiency gains lead to more total consumption, but the magnitude of this improvement is large enough to cause real near-term demand disruption.
So you're saying that even if long-term demand eventually catches up, because companies deploy bigger models or serve more users, in the short to medium term, companies can genuinely do more with the hardware they already have, and that delays new purchases.
Right, and here's the thing that I think is even more consequential in the long run. TurboQuant could fundamentally democratize access to large language models because suddenly you don't need a massive GPU cluster to run frontier-class AI.
That's the part of the story that I find most exciting, because right now there's this enormous divide between the companies that can afford to run these huge models and everyone else, and compression like this narrows that gap substantially.
Imagine a startup or a university research lab that previously could only run smaller open source models because they didn't have the budget for hundreds of H100 GPUs. Now with TurboQuant, they might be able to run much larger models on a fraction of the hardware.
And that has massive implications for the open source AI movement too, because if you can compress models like DeepSeek or Llama down to run efficiently on more modest hardware, you get a much more vibrant and competitive AI ecosystem overall.
Absolutely, and I think that competitive dynamic is part of why this matters so much strategically for Google, because they're essentially creating tools that make AI cheaper for everyone, including themselves, while simultaneously disrupting the hardware supply chain.
And let's talk about the academic credibility of this work too, because I think that's important context. This isn't just a blog post or a press release. These are peer-reviewed papers being presented at some of the most prestigious AI conferences in the world.
Right, so TurboQuant is being presented at ICLR 2026, which is one of the top 3 machine learning conferences globally. And the underlying QJL and PolarQuant papers are being presented at ASTATS 2026. So this has serious academic rigor behind it.
That level of peer review gives me a lot more confidence that the results are real and reproducible, because we've seen plenty of compression claims over the years that didn't hold up under scrutiny or only worked in narrow specific conditions.
And what makes this particularly robust is that TurboQuant doesn't require any retraining or fine-tuning of the original model. It's a post-training compression technique that you can apply to any existing large language model essentially as a plugin.
That plug-and-play aspect is huge because it means adoption can happen incredibly fast. You don't need to retrain your models from scratch or change your architecture. You just apply TurboQuant to your existing inference pipeline and immediately start saving memory.
Exactly, and that's why I think we're going to see this adopted across the industry very quickly, because the barrier to implementation is low and the payoff in terms of cost savings and performance improvement is enormous and immediate.
Now let's zoom out and think about what this means for NVIDIA specifically, because they're in an interesting position here. On one hand, their GPUs benefit from running more efficiently. But on the other hand, customers might need fewer of them.
NVIDIA is in a fascinating spot because TurboQuant makes each individual GPU more valuable and capable. But it also means that the total number of GPUs you need for a given workload goes down, so the net effect on their revenue is genuinely unclear.
And NVIDIA has been the biggest beneficiary of the AI infrastructure boom. Their stock has been on an absolute tear. So any indication that GPU demand might soften even slightly is something investors are going to watch very closely going forward.
I think NVIDIA will be fine long-term because the total AI market is growing so fast that efficiency gains get absorbed by new use cases and new customers. But in the short term, this creates real uncertainty, and that's reflected in the market reaction we've seen.
Let me ask you about the broader implications for AI development, because if memory is no longer the primary bottleneck, does that shift where companies invest their R&D dollars and what problems they focus on solving next?
Absolutely, and I think we're going to see a shift toward longer context windows, more complex multi-agent systems, and real-time AI applications that were previously too memory-intensive to be practical. because TurboQuant removes a major constraint.
That's a really interesting point because if you free up all that memory headroom, suddenly you can do things like run multiple specialized agents simultaneously or maintain much longer conversation histories without the cost becoming prohibitive.
And think about what that means for enterprise AI adoption, because one of the biggest barriers for companies has been the infrastructure cost. And if you can cut that in half or more, the ROI calculation for deploying AI changes dramatically.
I also want to mention the vector search implications because TurboQuant isn't just about language model inference. Search Engine Land reported that it significantly improves vector search speed too, which affects retrieval augmented generation and enterprise search products.
That's a great catch because RAG systems are becoming the backbone of enterprise AI. And if you can make the vector search component dramatically faster and cheaper with TurboQuant, that improves the entire pipeline from retrieval to generation.
So when we step back and look at the full picture here, Google has essentially published a breakthrough that makes AI cheaper, faster, and more accessible while simultaneously shaking up the financial landscape of the entire semiconductor industry.
And they did it with elegant mathematics rather than brute force hardware innovation, which I think is a really important signal about where the next wave of AI progress is going to come from. It's going to be algorithmic efficiency, not just bigger chips.
That feels like a really important theme for 2026 broadly. The idea that we might be entering an era where software innovation and efficiency and compression matters as much or more than just throwing more compute at the problem.
I completely agree, and Google is particularly well-positioned here because they have both the research talent to develop these algorithmic breakthroughs and the massive infrastructure to benefit from deploying them at scale across their own products and cloud services.
Any final thoughts on what people should be watching for in terms of TurboQuant adoption and impact over the coming weeks and months as the industry digests this and starts implementing it at scale?
I'd watch for 3 things specifically. First, how quickly cloud providers like AWS and Azure integrate TurboQuant-style compression into their managed AI services. Second, whether memory chip stocks recover or continue declining. And third, whether we see open-source implementations that let smaller companies benefit immediately without needing Google's infrastructure.
That's all for today's episode of the DX Today podcast. Thanks for listening, and we'll see you next time.